Array literals. Array literals are another type that is supported by Solidity. They are comma-separated list of one or more expressions enclosed in square brackets, which is really how arrays are represented in Solidity. These are always statically sized memory arrays whose length is the number of expressions used within them. The base type of the array is really the type of the first expression on that list, such that all other expressions can be converted to the first expression. If that is not possible, then it is a type error and indicated by Solidity. Fixed size memory arrays cannot be assigned to dynamically sized memory arrays within Solidity. So these are some aspects to be kept in mind when using array literals or when evaluating contracts that have array literals. Let's now talk about the gas costs of operations on storage arrays. Arrays, as we talked about, have push and pop operations. Increasing the length of a storage array by calling push has constant gas costs because storage is zero initialized, if you recall. Whereas if you use pop on such arrays to decrease the length of the array, then the gas cost associated with that operation really depends on the size of the element being removed. If the element being removed happens to be an entire array, then it can be very costly because it really includes explicitly clearing the removed elements, which is similar to calling delete on each one of them. Solidity supports the notion of what is referred to as array slices. Array slices really are views that are supported on contiguous array portions of existing arrays. They are not a separate type in Solidity, but they can be used in intermediate expressions to extract useful portions of existing arrays as required by the logic within the smart contracts. These are written as x start colon end, where x refers to the array, and start and end are the starting point of the slice and the ending point. So the first element of the slice is x of start and the last element is x of end minus 1. From an error checking perspective, if start is greater than end or if end is greater than the length of the array, then an exception is thrown. Both these start and end values are optional, where start defaults to 0 and end defaults to the length of the array. Array slices do not have any members that are supported, and for now, Solidity only supports array slices for call data arrays. Let's now talk about struct types. This is something that we discussed earlier. Struct types in Solidity are another user-defined types. They're aggregate types, which means that they let the developer combine different variables of value or reference types into one unit and treat them together in the contract logic. So these are used extensively within smart contracts, very commonly encountered in really almost all smart contracts that you would see in Solidity. Some of the properties of struct types are that they can be used inside mappings and inside arrays, and they themselves can contain mappings and arrays. So all these different complex reference types can be used in a very interrelated manner and really allows for versatile usage of these data structures to support different kinds of encapsulation logic when it comes to the different data types within a smart contract. There's one exception: struct types cannot contain members of the same struct type. The third and unique reference type within Solidity is the mapping type. Now let's move on to the mapping type, which is an interesting reference type supported by Solidity, somewhat unique to Solidity. These mapping types define key value pairs. and they're declared using the syntax as shown here, where you have a mapping keyword followed by a key type and a value type, and then the variable of this particular type. The key type in a mapping can be really any built-in value type, byte, string, or any contract or enum type even. Other user-defined or complex types, such as mapping structs or array types, are not allowed to be used as the key type. So there are some restrictions here. On the other hand, the value type of that key value pair can be any type, including mappings, arrays, and structs. There are some interesting aspects of how mappings are created and maintained by Solidity. The key data is not stored in a mapping. It is only used to look up the value by taking a Keccak 256 hash of that key data. They also do not have a concept of length or a concept of a key or value being set in the mapping. They can only have a storage data allocation, so they're only allowed for state variables. They cannot be used as parameters or return values of contract functions that are publicly visible. So these are some of the restrictions. They're also true for arrays and structs that contain mappings, not just mappings themselves. Also, one cannot iterate over the mappings. You cannot enumerate their keys and get their resulting values. This is not supported by default, but it is possible where required by implementing another data structure on top of mappings and iterating over them. So very versatile type in Solidity, again, very commonly encountered in smart contracts to store associations between different data structures that are used in that contract logic. So something to be really paid attention to while evaluating smart contracts. Solidity supports the notion of what are known as shorthand operators, similar to many other programming languages. These are concise notations of slightly longer expressions as shown here. So instead of saying A is equal to A plus E, one can use the shorthand notation of A plus equal to E. Similarly, other arithmetic operations are also supported with this notation. There are similar shorthand operators for increments and decrements. A plus plus and A minus minus is an example. A plus plus returns the value of A, after which the operation of plus plus is performed on A. The counterparts are plus plus A and minus minus A, where the result of the expression is really the value of A after the increment or decrement has been performed. So these are again commonly used in smart contracts, and from a security perspective need to be paid attention to, because especially the A plus plus or plus plus A, an incorrect assumption could be made on the value being returned as a pre-increment or a post-increment, whereas the semantics is really the opposite. Solidity supports the delete keyword that can be used within smart contracts to reclaim the underlying storage of a variable when it is no longer required in that context of the contract. Applying this keyword on a variable A of a particular type assigns the initial value for that type to A. So if it is applied on integers, then the value of that variable is set to 0. For arrays, it assigns length of 0 for dynamic arrays, and for static arrays, the length remains the same, but all the elements are set to their initial value. Delete A of x, where A is an array and x specifies a particular index, deletes the item at that index of that array and leaves all the other elements and even the length of that array intact. For structs, delete assigns a struct with all the members reset to their initial values. Delete has no effect on mappings. This is an exception that has to be paid attention to. So if you delete a struct, which in turn has a mapping as one of its fields, then delete will reset all the members of that struct that are not mappings, and will also recurse into each of those members unless they are mappings. So mappings are left untouched, but if we want to delete a particular key of that mapping, then that is possible. So this is again used in smart contract logic to a certain extent, and from a security perspective, the aspect of delete to be kept in mind is their impact on the initial values and their exception for mappings where they have no effect. So far, we have talked about various types supported by Solidity, value types, reference types, and each of those categories containing several types themselves. And every programming language that supports different types supports this concept of conversions, where variables of different types can be converted between each other. There are two types of these conversions. Some of them can happen implicitly, where that conversion is applied by the compiler itself. And these typically happen where that conversion makes sense semantically and there is no information that is lost. So this is a very safe conversion that is applied by the compiler. And such conversions happen during assignments of variables, when variables are passed as arguments to functions, and the parameter types of those functions are of a different type than the arguments applied, and in other contexts as well. Examples of implicit conversions in the case of Solidity are converting a uint8 to uint16 or int128 to int256 and so on, where the resulting type is bigger in the sense of the storage supported than the type that is being converted from. So uint16 has 16 bits that can safely store uint8. However, exceptions to implicit conversions are converting from signed integers to unsigned integers, and that doesn't make semantic sense because unsigned integers cannot hold or represent negative values. The flip side of implicit conversion are explicit conversions, where the type conversions are explicitly applied by the developers themselves and not by the compiler. The reason for that is the compiler cannot deduce or prove the type safety of such conversions, and they may result in an unexpected behavior. There are various rules to such explicit conversions. In the case of integers, when they are converted to a smaller type, the higher order bits are cut off. When they are converted to a larger type, they are padded on the left with the higher order end. So these apply, for example, when uint8 is converted to uint16, the padding happens onto the left, and when a uint16 is converted to uint8, the higher order bits are cut off. Similarly, for fixed size bytes, the bytes arrays or bytes 1 all the way to bytes 32, converting to a smaller type cuts off bytes to the right, and converting to a larger type will pad bytes to the right. So these rules are something that the developer has to pay attention to when forcing explicit conversions, and if not done right, they could really result in undefined, unexpected behavior because the values, underlying variables, are chopped off in an unexpected fashion. Solidity supports conversions between literals that we talked about. They're possible between literals and elementary types. And there are various rules that apply. Decimals and hexadecimal number literals can be converted implicitly to any integer type that's large enough to represent it without getting it truncated. However, decimal number literals cannot be implicitly converted to fixed size byte arrays that we discussed earlier. With hexadecimal number literals, can be converted to fixed size byte arrays, but only if the number of hex digits fits the size of the bytes type exactly. There are some exceptions to this as well. String literals and hex string literals can be implicitly converted to fixed size byte arrays, but only if the number of characters matches the size of the bytes type. So these are various Solidity rules that need to be considered while converting literals, and again something that you might encounter while analyzing smart contracts. The next type that we'll talk about are what are known as Ether units. We talked about how Ethereum has a concept of a native currency called Ether, and Ether is 18 decimals. The smallest unit is a Wei, and there are various names given for different numbers of Weis, like 10 power 3 Wei, 10 power 9 Wei. There are different names given that we talked about in the Ethereum module. In the case of the Solidity types, a literal number can be given a suffix of a Wei or Gwei, a gigawei, which is 10 power 9 Wei, or an ether, which is really 10 power 18 Wei. And these are used to specify subdenominations of ether, as we see here, which are used when contracts want to manipulate different denominations of ether in the context of the logic. And this is again something that you will encounter when you're looking at contracts manipulating ether units. Similar to ether units, Solidity also supports the concept of time units. As you can imagine, contracts might want to work with different notions of time for various types of logic that they want to encode. Solidity supports different suffixes that represent time, and these can be applied to literal numbers. And these suffixes are seconds, minutes, hours, days, and weeks. The base unit for time is seconds. So literally, when 1 is used, it is the same as representing 1 seconds. 1 minute is 60 seconds, 1 hour is 60 minutes, and so on, as shown here. These suffixes cannot be directly applied onto variables. So if you really want to apply time units to certain variables, then one needs to multiply that variable with that time unit. So as an example shown here, if we have a days after variable and we really want it to represent the number of days, then we cannot apply the days suffix directly to it, but we have to multiply days after with 1 days. So that is really how Solidity allows one to use these units with variables. Solidity allows accessing various block and transaction properties within smart contracts. These allow developers to perform interesting logic that are dependent on different aspects of the current block or the transaction. So in the case of the block, we have the block hash that gives the hash of the specified block, but only works for the most recent 256 ones, otherwise returns 0. There is block chain ID, which gives the current ID of the chain that this is executing on. There is the block number, which is the sequence number of the block within the blockchain. There's the block timestamp, which is the number of seconds since the Unix epoch. There's also the Coinbase address, which is controlled by the miner, and the beneficiary address where the block rewards and transaction fees go to. There is the block difficulty related to the proof of work. There's a gas limit related to the block. And there are also fields related to the message value representing the amount of ether that was sent as part of this transaction. Message data, which gives access to the complete call data sent in this transaction. Message sender, which is really the sender of the current call or the message, and the message signature, which is really the function identifier or the first 4 bytes of the call data representing the function selector that we talked about earlier. Then there are transaction components of gas price used in this transaction, the amount of gas left in this transaction after all the computation so far, and also the transaction origin, which is the sender of the transaction, representing the EOA, if you recollect from the Ethereum module. Let's talk a bit more about message values. Message value represents the amount of ether sent in Way as part of the transaction, and message sender is the sender's address. The thing to be kept in mind is that every external call made changes the sender, and every external call made can also change the message value. So if we have 3 contracts, A, B, and C, where A calls B and B calls C, in the context of the contract B, the message sender is A, but in the context of the contract C, the message sender is contract B and not A. These aspects should be kept in mind when analyzing the security of smart contract, because the developers could have made incorrect assumptions about some of these that could result in security issues. Let's now talk about randomness sources. The block timestamp and block hash that we just discussed are not good sources of randomness. That's because both these values can be influenced by the miners mining the blocks to some degree. The only aspects of timestamps that are guaranteed is that the current block's timestamp must be strictly larger than the timestamp of the last block, and the other guarantee is that it will be somewhere between the timestamps of 2 consecutive blocks in the canonical blockchain. Therefore, smart contract developers should not rely on either the block timestamp or the block hash as a source of good randomness. Let's revisit the concept of block hashes. Solidity supports a block hash primitive where the block number can be specified to obtain the corresponding hash. This is possible only for the most recent 256 blocks, excluding the current block. For all other historical blocks, the value returned is 0. So as you can imagine, this becomes important when you're considering the security aspect of code using this primitive, because the block number should really be the most recent 256 blocks. Otherwise, a value of 0 is obtained. Let's move on to the ABI encoding and decoding functions supported by Solidity. Solidity supports multiple functions in these categories. The obvious ones are the encode and decode functions that take arguments and encode them or decode them specifically with respect to the application binary interface. There are also functions that encode with the function selector or with the signature that we touched upon in some of the previous slides. And finally, there is an encode packed function that takes the arguments and performs the encoding in a packed fashion. So there's no padding applied between the arguments supplied. And for this reason, the packed encoding can be ambiguous. This is something that affects security when you're considering these functions, specifically this encode packed function, and we'll revisit this when we take a deeper look in the security module. Let's now switch gears and talk about the important concept of error handling. Error handling is really one of the most important, fundamental and critical aspects of programming languages security. And the reason is that errors during program execution are what result in security vulnerabilities. These could be errors resulting from user inputs when they interact with the smart contract, and the inputs are not as expected by the developer during the coding of the contracts. These errors could also be due to assumptions made within the smart contract that are not really valid for the various control and data flows that happen during program execution. These could also be related to the program invariants that are expected from a specification perspective, and these invariants might not hold good during certain control and data flows. Solidity supports multiple primitives for error handling. The first set of primitives are functions that let the developer assert or require certain conditions to be held. The assert primitive, for example, specifies a condition as its argument, and if that condition is not met, if it evaluates to false during runtime, then a panic error is raised. And this panic error really reverts all the state changes made to the contract logic so far in the context of the transaction that triggered this contract. And this assert is really meant to be used for internal errors, for program invariants that are meant to be held at any part of the program during execution. This is in contrast with the require primitive, that is another error handling primitive supported by Solidity, which also specifies a condition that gets evaluated at runtime. And if that condition evaluates to false, as in it fails, then it again raises a revert that reverses all the state changes made to the contract so far, similar to the assert primitive. And compared to the assert primitive, the require primitive is really meant to be used for errors in inputs from users or from external components that the contract interacts with. The require primitive takes an optional string as an argument. This is a message that gets printed if the require condition is not met. And finally, there is a revert primitive that unconditionally aborts execution when triggered, and it reverts all the state changes similar to when the conditions are not met for assert and require primitives. This again takes an optional string that gets printed when that happens. And the thing to be kept in mind is the difference between assert and require. Asserts, to re-emphasize, are meant to be used for internal errors, conditions that are really meant to be true as program invariants throughout the execution of the smart contract. And this raises a different type of error, which is the panic error that we'll look into in more detail later on. Require, on the contrast, is meant to be used for external errors, errors coming in because of user inputs or errors resulting from interactions with external components. Require takes an optional string, whereas assert does not support this optional string. So these are some of the differences that really, as a best practice, require developers to use require as opposed to assert in many places within the contract for error handling. There were some historical differences as well in the use of a particular opcode, a different opcode for assert versus require, that affected the gas consumption. But some of these have been changed in the recent Solidity versions. Let's now talk about the math and crypto functions supported by Solidity. Solidity supports the addition and multiplication operations with modulus, addmod, and mulmod. It obviously supports the Keccak 256 hashing function that is really fundamental to Ethereum and used extensively within multiple aspects of Ethereum and within the smart contracts themselves. It also supports the standardized SHA-256 algorithm related to Keccak, but the standardized version. It further supports one of the older hashing function, the RIPE message digest, for historical reasons. And finally, it supports what is known as the EC recover primitive. This is the elliptic curve recover function that takes in the hash of a message as an argument along with the signature components, the ECDSA signature components of V, R, and S that we talked about in the Ethereum module and even earlier. EC recover takes in these arguments and returns the address or recovers the address associated with the public key from the elliptic curve signature that is specified in the parameters. This is used in various smart contracts, again, to recover the address and use it for different types of logic within smart contracts. This has a security implication, which we will talk about in the next slide. EC recover is susceptible to what is known as malleability, or in other words, non-uniqueness. In the context of signatures, this means that a valid signature can be converted into a second valid signature without requiring knowledge of the private key to generate those signatures. And this, depending on how signatures are used within the contract logic or the reason why the signatures are used within that contract logic, can result in replay attacks where the second valid signature can be used by the user or even by the attacker to bypass the contract logic that is using these signatures. The reason for this malleability is the math behind how elliptic curve cryptography works. So the signature components of V, R, and S, the S value can either be in the lower order range or in the higher order range. And EC recover does not prevent the S value from being in one of these two ranges. And this is really what allows the malleability. And if the smart contract logic using EC recover requires the signatures to be unique, then the best practice is currently to use the ECDSA wrapper from OpenZeppelin that enforces the S value to be in the lower range. So it really forces there to be a single valid signature for the signature component.